Thank you. I thought if I was clever, I could make this introduction last for about 50 minutes, and I wouldn't need to write my slides. I'll keep this to a minimum. Yes, as was introduced, I have a pilot's license. I got it when I was 23, and I still tend to use it as I fly around the world. I go on business, and if I got a weekend, I'll pick up a plane and try to use it. This is New Zealand, landing on the beach. This is what's called White Island. It's a volcano just off the north coast of the North Island, about 50 miles off the north coast. It's quite spectacular, it's still smoking, as you can see. It's flying over Sydney. There's a lot of superb cities. I'll show you another one in a second, but it's amazing to be able to see beautiful cities like this from the air and be able to sort of fly around them and see them in any way that you want to see them. For those familiar with Ayers Rock, this is right next door. When I say right next door, it's about 30, 40 miles away. It's about 600 miles from Alice Springs, right in the middle of the Australian desert. It's called the Olgas, absolutely stunning. One of my favorite pastimes when I'm not flying is at the pub. This is combining both. This is a little place called William Creek, which has a population of 2. It's about 700 miles from the nearest town, which has a population of about 10. Basically, you land on the road, pull up at the pub, and drink. And this was New Year's Eve. There was a lot of other people there that flew in. A few people who drove in for literally a day. Plus, the nearest farm to this is 1/3 the size of Texas. So when Americans say things are big, this puts it into perspective. Anyway, sort of land and take off on the road. That was fun. If anybody knows Ross Mason, this is me taking him up in San Francisco. Ross Mason's the founder of MuleSource. So this was last year, basically pottering around in San Francisco. And last slide, to say it's you get some pretty spectacular views. I'm always tempted when I see big bridges like this to be able to fly under them, but it's a very quick way of losing a license. But anyway, just that was a quick introduction. What I'm going to go through today, give you a little bit of background. I set out to, when I wrote these, or originally set down to write these slides, I thought we can go into some really great detail of the JVM and some of the settings and things. And anybody that's tried tuning will know that every single setting on the JVM, and there are literally dozens and dozens of them, and obviously the combinations, there are thousands, tens of thousands of combinations. Everyone is precise for your one application on one particular architecture, running one particular set of work in one particular scenario. So whatever I tell you is going to be pretty useless when you go home. So I thought I'd go back to some of the basics. And last week I spent, as I usually do every few weeks, over in the US visiting clients. And one of those clients had a performance problem. And you expect to go over and sit there with your head deep in the JVM, debugging, etc. And there were 2 parts that I discovered very after a day or so, maybe on the second day, when we were just basically learning the architecture of what they were doing with our product, that it suddenly dawned on me, if I'm going to go and do a talk on performance tuning, we should really go back to some of the basics on this. And the reason being is that we're getting 10 times performance increase just by looking at some of the architecture and some of the silly things that have been done. And I'm sure a lot of you know these, but it's I hope not everybody knows all of these things, otherwise you're not going to learn very much. But I hope I'll be able to drill some of these in. I've spent a long time since the beginning of Java and a good decade before that in C. So there's a lot of experience in here in terms of things that are important for tuning. And I will go into the JVM and I will go through some of the memory allocations and how those work towards the end. But I want to spend a bit of time on going back to basics if I can. To give you an idea of the problem, it's my typical client. We're sitting there, they're trying to process typically trade data, payment data. For those that know the technologies, FIX, this comes off the exchanges, FPML, ISO 20022, SEPA, which is a single European payments area, SWIFT is payments, etc. And they're getting very large amounts of messages. If you're looking at ticker data, which is price data from the exchanges, we're looking at hundreds of thousands per second. The CME hit 350,000 a second recently. That's not typically lasting very long, but we're looking in the high tens of thousands into the hundreds of thousands. And if we're looking at trade confirmations, we're down into the sort of low thousands per second, etc. So give you an idea of the sorts of stuff we're trying to process. Most low latency traders, etc., will do this in C and C++, but of course we're here and we're looking at Java, and this is what I'd like to go through, some of the performance aspects and problems. Now, before we touch on performance, it's not just about making things go faster. Latency is important. It's one of the areas where a talk I did a number of years ago, where just before somebody had quoted on the New York Stock Exchange that 1 millisecond was worth about $100 million. I'm sure you can do the calculations, but that's roughly what it's worth in terms of latency. This is why they put the machines actually physically in the environment that they're working on, because of the speed of light time. 1 millisecond is about 300 kilometers. And Amazon, I found an interesting section here. They reckon that about 100 milliseconds of delay on an e-commerce site is worth about 1% of their e-commerce business. So again, you know the size of Amazon. That puts it into perspective, just how important this is. And then finally, for those of you that don't work in a large banking environment or a large company, it's not the cost of the software so much, it's not the cost of the machines. Everybody knows you can go out and buy a decent server for a reasonable price, and of course if you're in a company they'll charge you more. It's the cost of running these in production. If you look at the average life cycle of an application, you design it, you develop it, and then it stays in production, one would hope, for 3, 4, 5, 6 years. And many businesses will charge, and I'll use dollars because it's the number that I was quoted, it costs about $20,000 per year per machine to host these. That's the cost of the environment, the air conditioning, the people to run these things. So that's the cost of one physical machine. So if you can reduce that, this is the sort of thing that we're going to get, where we're aiming for this. So I'm not going to give you any silver bullets. There is no Java machine parameter that I can basically quote you that will make all of your applications run twice as fast. I'm sorry about that, but I will hopefully give you enough information that you can start tweaking some of this for those that haven't played with the JVMs, or for those even that have, but hopefully give you some ideas to go back in and look at what you've done. So what I'm going to try and give you out of this is some ideas and enough information to go back and do a little bit of tweaking. I want to go back about 20 years. I used to teach, well, not quite 20 years, 15 years ago, I used to teach for Learning Tree, Java. And we used to have this section. Does anybody recognize this very pretty fractal? It's called a Mandelbrot fractal, and a few of you do. Back in about 80s, early 80s, everyone had T-shirts. It was the big thing that came out, so it was very colorful. We used to demonstrate, as part of the Java course, basically, if you wanted to make Java run faster, you had to use JNI, the Java native interface, and then you had to call C, because C basically ran stuff faster, and you come back into Java afterwards. So this was one of the exercises we did, and effectively what happens for every single pixel on the screen, in that particular one there, which is probably about a 600 by 400 resolution, each one of those represents a real and an imaginary number, i.e. a complex number. And basically, to get the color, you do a number of iterations, and the amount of iterations that go before you reach a certain point dictates the color that you're going to get. The formula is beautifully simple. There's a little bit of Java code there. Effectively, you just pick a point. The point is determined by the pixel, effectively, imaginary on the vertical axis and real on the horizontal axis, and you iterate a number of times. Iterate typically 1,000 times, it's black, etc., etc. A few years later, at about 2000, it became apparent that this wasn't running much faster, and it became a good demonstration of why not to use JNI, why you would avoid JNI, because by this time, Java had started to catch up. And I think this was the turning point where Java became a novelty language to animate your GIFs, which was about, remember the internet was just coming out, so the late 90s we had GIF images. You were starting to get images inside your internet, because previously it was email before that, and the Usenet, and porn obviously. And you could start to animate things. And this suddenly started to become useful in the server side. Today we can probably render the same thing. I've seen some pretty impressive bits. You can put this even on iPads or iPhones, render it in sub-second on far superior resolutions. The sort of thing now that you can render in 3D on a 1080p screen. It still, however, requires a lot of calculations. The number doesn't come down, but as people have got to understand this fractal, they've got to optimize it. And what's most important is that the optimizations on this have almost exceeded the actual performance enhancements of some of the machines. So the combination of the two have resulted in a lot of performance. And on day-to-day work, however, we're doing a lot of data processing, and it's the data processing that I want to hook into today. So again, just as a reminder, I want to go back to some of the sort of earlier forms of coding. I'm sure a few of you remember Pascal. Anybody learn Pascal when they were kids? That's most of it. Or even recently, actually. As you probably know, Pascal string has the length of the string right at the beginning. It's a little bit of a restriction. It means that you can't have strings particularly long, but hey, Twitter managed to make a business out of it. And fairly simple, it worked. And concatenation, etc., was relatively easy. If you wanted to get the string length of this, you simply just look at the first byte, really, really quick. Looking at C, we have the same memory, but effectively we have a null at the end, so a 0 character at the end. Now, if you want to get the string length of this, obviously you've got to now iterate through the entire string until you find the 0 at the end. So it's indeterminate until you reach the end. Lots of different advantages and things. And both of these, Pascal and C, are very, very simple when you're processing them. There were a few restrictions. Remembering these were bytes, not characters or chars as you get in Java. As Java, 7 or 8 have now changed, it's not even 2 bytes per char, they've gone into 3 or 4. What effectively this meant that we couldn't actually use the A with the little, I'm sure you have a name for it in Denmark, the beginning of Aarhus. Got a name? Oh, thank you. One of those. We couldn't use it in the earlier days because they simply didn't exist in those character sets. You actually had to predetermine the character set before you went in. So when we're working with C, it made it relatively easy, but also because we were working at a very low level, we're just off machine code here, so we're just off the assembler level. When we wanted to actually do something very fast or do something that we were doing a lot of or iterating, we could manipulate the memory in exactly the way we wanted to do it. So if we wanted to call into a function and the function, and I use the word function as opposed to method because methods come off classes. So if we called into a function, we could actually modify the string in the function without having to return it afterwards and therefore copy it each time and create new versions. So if we wanted to manipulate the message, we could pass it into a function, the function could manipulate it. And it was relatively simple. And also it meant that when we passed the string, we just needed to pass a pointer to it. And then, of course, you could put a const, which meant that you weren't allowed to actually change the content of it, and that was a bit like what we have today. And so as we move forward into the object-oriented languages, we start to effectively put more functionality into these strings. We came away from the byte array, or the char array as we know it, and we started to create an object around these, and we started to abstract ourselves because we're in an environment where we want to abstract things, and we abstract ourselves away from the underlying machine, which in some ways is good, but in other ways it's not quite so good when it comes to performance. If, for example, we wanted to pass a very large string or a large chunk of memory, we didn't need to do it. We just needed to effectively pass a pointer to the same place, and that was it. We didn't need to copy it. If we wanted to copy it, because we knew it was memory and we knew it was contiguous, we could use a memcopy or something. We could actually copy that in a much more efficient way. And then some interesting things happened as we moved into C++ and Objective-C. Before the standard libraries came around, we had collection classes. We had sets, maps, lists, linked lists, etc., and different derivations of those things. It was quite interesting because there were lots of different versions around and they weren't standardized. And one of the interesting problems was if you created a string and you put it into a collection, who owned the memory of that string? So if the string goes into the collection and then you delete the string, or you basically you didn't have a garbage collector, but you freed it to allow the memory to be used elsewhere, it was good programming practice. The problem was that the collection had a copy of the same bit of memory. So if you came to use that, you'd get lots of corruption. So we'd have these, what Windows used to have, the general protection faults, etc. So this became an issue, and you could imagine putting something into a collection, into a set, and then something would delete it out of that. So whether it was the putter or the getter that deleted it, or even the list itself that managed it in a different way, took a copy and deleted it, we had some rather strange things happening. So we started to create these objects which became immutable to make life easier, and then of course along came memory management. So when the memory management came along, generally it did a better job than your average programmer. Fortunately, this was the era when Visual Basic and things came along and people thought they were programmers, and would effectively go out and get jobs, and somebody say, okay, the Visual Basic's really good, now I want to put you on C, and we get an awful lot of problems. So memory management is good for the lower end of the programming hierarchy, shall we say, but for those that were used to being able to manage the memory, it created a few issues. If we go to strings in Java today, and I'll get to the point in a second, if we go to strings, the message comes off your JMS, so you read a file and you read these into strings, and you need to now process this. So a very simple one here, I've got the alphabet, and we need to pick little bits out of this alphabet. Now if we pass the string around, that's fine, but if we want to take little bits out of this string, for example, we do alphabet.substring, or even if we pass the alphabet in and then we do a substring afterwards, don't forget we're getting tens of thousands of messages a second, and we might be running multi-threaded, and all of these start to create Java objects, and it's these temporary Java objects with the strings that start to cause the problems in the JVM. Now you could get to this attitude where you could say, oh, the JVM is going to take care of it all. That's fine, you know, I'm used to this. You can basically write your code, the JVM comes along, does all the garbage collection, and it's pretty good at that. And I think what's happened is people have got lazy. People who have not used or had the experience of just how fast the machines are that we have today, going back to that Mandelbrot set, we were processing, what did I say, in a VGA screen, 768 or 700,000 floating point operations a second. Now in those days, your machines would run at about 5 megahertz. 10 megahertz for a faster one, and then you had a floating point unit behind that. Now, that meant that you were getting maybe 10 million 10 million instructions per second, but floating point instructions, you were looking at about 1 million per second. So if you wanted to do a 1080p screen and run it 1,000 times, you were looking at sort of 20 minutes to process this. Obviously, 1080 wasn't around then. People have forgotten how fast these machines are that we have today. Your average laptop is 2 point something gigahertz, sometimes 3 gigahertz. You've got a floating point unit built into the processor, a co-hosted processor, which is typically chucking out over 1 billion floating point operations per second. So when I go to these clients, sometimes they're sitting there saying, it's really cool, we're getting 200 transactions a second out of it. My brain thinks, hang on, 1 billion floating point operations a second, you're getting 200 out of it. What on earth is it doing for the rest of the time? It's just not possible to go that slow. Who here can remember, let's say early 80s? It's not a test of how old you are, but I mean, we had machines, maximum speed 4-6 megahertz or something. We used to get really pretty cool games out of those things. You had to sit and type for days and days out of a magazine to type in all of the stuff. You used to get amazing stuff out of that. And it got faster and faster and faster. People have forgotten that. So let me give you an example. If I have a 1 gigabyte file, it's pretty big. It'll fit on most USB drives these days. If I'd asked the same question 5 years ago, you'd have thought, wow, it'll take up half my disk drive. Now you want to, it's got 1 million rows in there. Each row is roughly 1K in size. 1K is about 4 tweets. Okay, so put it into perspective. Just so you understand what it is. So you've got 1 million of these things. Now inside that, so we've got 4 million tweets, if you like. We need to find one particular piece of information, and we chuck this into a JVM, if we like, or we can use any other language. How long do you think it will take to find that piece of information out of 4 million tweets? Less than a minute? Go on, show of hands, please. More than a minute. Anyone? Oh, someone's scratching that. That's right. It's not. Less than 10 seconds? Less than a second? It should be less than a second to go through. I mean, I gave you the performance on this. The funny thing is, if you actually run it in Java, it typically on an average machine, it takes quite a bit more than 1 second, even if you're running NIO. But if you run this as a standard Unix command, as a grep or something, you can typically get less than a second in performance out of this. And people are engineering these incredibly large, complex systems that are taking literally 30 seconds to do this sort of computational search. People are forgetting the sort of performance that we've got. So this is, when I turn up at a client, I look at these things and think, no, you're an order of magnitude, maybe 2 orders of magnitude out of how fast this should be going. So this is why I often sit down and look at the architecture. Now, this isn't necessarily the solution. I had a chat with my colleague outside, and we could take something relatively simple like this, and I'm sure between everyone here, we could come up with probably 24 different solutions about how to optimize this. It's meant to be an example. So if we take the one here where we're trying to take some information out of it, now what I'm trying to do is basically take a large complex message and extract all of the information out of that message and put it into a Java object, which has a whole bunch of private fields where I've got getters and setters. What I'm trying to do is populate that as fast as possible and make it available for somebody who now wants to sort or put these objects into collections and basically treat them as Java. So effectively, I'm parsing the string, putting it into Java. Now, if I call the alphabet.substring, I create a new string, albeit a very small string. It's a string with 1 byte in it, and then I pass it to the function. The problem is it's a string. The overhead of a string is far in excess of the 1 byte that I'm creating. Now I could pass the string itself. If I pass the string itself, it's passed by reference. If I modify the string, it's immutable, so it creates yet another string. Now if I just want to take the information out of it, the very quickest way to do it on this, incidentally, is to effectively pass the string, and inside my method is to use a string.char at, get the index of the char, and then effectively, if I can, cast it to a byte if I want to store a byte or a char. Out of interest, how long do you think it would take to run 1 billion of these sitting in this little loop here? 1 billion, that's 1,000 million. For those that are out of touch with billions, Americans used to have different billions from the English. So we'll qualify this 1,000 million times just on this one thing. Greater than 10 seconds? You're all sitting there with calculators now. More than a second? Actually takes on my laptop 0.06 seconds. It's quite impressive. 1 billion times to run on this. Now, if I'm extracting all this information out of here, I want to get this far more performant. So that's the sort of thing that I'm going into. The reason I wanted to bring this up is because this was a typical problem we had. We were parsing fixed messages, and the original parser was in fact, or the code was generated, and the parser was relatively naive, and it used to basically say, what am I looking for here? Using reflection, and it would go across and it would look up the information that it's got and then effectively do a set, and basically it would run through and parse it as strings. We never really realized that it was an issue because we were quite happily doing a few thousand a second. It became apparent when a client needed more than a few thousand a second, and all of a sudden we started to look at the parser. We got that parser from a few thousand a second up to 138,000 a second. just by optimizing out these sorts of things. Now, this is not the sort of thing that you can get out of JVM tuning. So it's something that I want to sort of put forward when you're looking at the architecture of your system to effectively try and look at some of these smaller things. It's very easy to take a very small part out. If you can create some JUnit tests or whatever test framework you like, take out some of the areas that you're looking at, profile what you've got, and I'll go through some tools at the end that we can look at. And then start to optimize how you can sort of, you may find that this is sort of inherent right across your architecture and the usage of this, so it may take quite a bit of extra work. Is there a question there? It wouldn't work with, sorry? Wouldn't work with the Danish letters, yes. On bytes, you're right. If you were doing chars, it would. You'd be fine. I think I did point that out, but it's yeah. If you were doing chars, yeah. If you're doing bytes, obviously you're going to be chopping off anything that's non-ASCII. But unfortunately, the Americans got there before we did, or before you guys did. If the Danish had invented the alphabet for computers, it would have been different. Perhaps we wouldn't have 8 bits in a byte, we'd have 10 bits in a byte or something, I don't know. Binary bytes, that'd be interesting. Here's another interesting one, at a client. It's another thing that sort of got me thinking about this. So sitting down at a client site, this is one of the things that got me thinking, why should we go directly into the JVM? So looking at the client system, it's got some way to go yet. It's got another few weeks. They're not really into the tuning or such yet. They're basically just finishing it off. It's some way short, not quite a tenth of the speed that it needs to run at, but it's some way short, and they're scaling this up, and it's a distributed architecture. And this thing's running, and I won't quote any numbers because if these guys watch this video afterwards, they'll realize I'm talking about them. But let's say it's running a certain throughput per second. So we look at it, and just having a quick look, how much memory has it got, what's it working on. So it's got 4 gig of RAM. I'm thinking, well, it's pretty good. There's not much doesn't run in 4 gig of RAM. That's a lot. The JX-MX was 4 gig. JX-MS, we'll go through these in a second, was 2 gig. Fine, no problems at all. No other parameters, running minus server. Thought fine, so I did a little PS minus EF, which basically gives me all the parameters from everything running on the machine, just to see what sort of user and system throughput it's picking up on the CPU. It's got 2 CPUs in there. They're both running relatively fast. It's running on Linux. And I find another Java virtual machine running in there. And interestingly, it's running Tomcat. And that's running 2 gig. So we've got 4 gig on one, 2 gig on the other, plus, of course, the operating system and all the bits. That machine was actually only had 4 gig of RAM in it. It was a virtual machine. So combined the 2 virtual machines, 2 JVMs, plus the operating system, we had 6 gig of RAM trying to run inside a 4 gig machine. Now Linux allows you to do that, and it simply just swaps it out. Problem is, when it swaps, it goes to disk. So all of a sudden, we end up with these, what's normally fairly quick running in memory, now running on disk. And of course, this has a very major impact on the performance. Something incredibly simple, but because the programmers had written their application to run an environment which they were very sure about, and they said it's very easy, you just give it this much memory, and they pass it on to operations. And of course, operations say, well, the programmer told me it needs this and that, etc., but they hadn't actually thought about how everything combines together. Easy mistake, and quite silly when you see it, but it certainly made a huge difference to the tuning. So effectively, if you're hitting the high memory barriers, we were getting or looking at about 2 orders of magnitude out of that one. And you could sit and debug that forever, and you're not going to find anything. It's effectively the overall system that dictates how this runs. Another example of over-engineering, I thought this was quite amusing, and had quite a long chat with the guys on this one. Now they're trying to save, let's say, 20,000 messages a second. Now the architecture is, you read the messages off a queue, you safe store them, you pass them onto another queue, so it's nicely stepped out architecture. It's distributed, put things into queues so you can distribute them nicely. And they've got a safe store. So 20,000 messages a second, over 8 hours of trading. I'm reading the numbers off the screen here. We're looking at roughly 20 meg per second, or 72 gigabytes. So they decided to use an in-memory database. There's lots of them. I won't name the one in this particular case. But unfortunately, as they got towards the sort of pre-production trials, there was no problem with their architecture. There was no problem with the tools they were using, apart from the fact that they didn't have enough knowledge of how to run them. But they then had to get lots of people in to try and tune this to get it working. And what they were trying to do was to get this in-memory database working across and sharding and doing everything it should do to be able to run at this sort of performance. Now, it's not particularly fast performance, but it wasn't working and it was creating lots of issues. And also, when they ran things through several times, they retried them. They had to then go back to the database. They had to clear it out. If they stopped everything, they lost the rest of the day's work, etc. So it got more and more complicated. My question was, why didn't you use disk? 20,000 messages a second. You can write out to even a hard disk. What are the old, those spinny round things that go rusty when you leave them too long? We're on SSD. A lot of people are on SSD these days. From SSD, you can write 2 gigabytes a gigabyte every 2 seconds. So there is absolutely no problem of writing all this stuff to disk. So for a safe store, we've got clients that are taking these messages off an average of 100,000 a second, and they're writing these to disk. So my point is here, simplicity. If you want to get people to manage disk, if you want to replicate the disk, it's much, much easier than trying to get people that are qualified in this in-memory database. That was really a sort of a sideline, but it was another thing that sort of got me thinking about, why are people trying to over-engineer these solutions? So I want to look at the JVM. What I want to try and get out of this is just give you, I can imagine there's quite a few people in here that know quite a bit about the JVM, but hopefully there's quite a lot of you that just treat it as a fairly black box, and this should hopefully give you a little bit of information about how you can, there's a few parameters that you can tinker with and play with that will make quite a difference in the performance of your machines. So first of all, it's divided into 2 main sections. We've got what's called the permgen, permanent generation. This is where the classes are loaded up. So if you're doing object relational mapping, you're messing around with XML, you're doing JAX-B or something like that that's generating huge amounts of classes, sometimes an IDE that's loading up all of your code, you'll very quickly run out of permgen space, and you'll get an out-of-memory permgen. And the very simple parameter for this one is just to basically set the permgen size. 250 meg should see you through most usages. It's not something that's going to change the speed of your virtual machine. It is garbage collected, but it's not going to make a massive amount of difference. As things are loading up, they're fairly slow because they're loaded up from disk anyway, typically, even if it's flash drive or something faster, SSD. So it's not going to make a massive difference, but this is one of those things that either goes or it doesn't go. Now, the more interesting part is the heap. Now, there's 2 parameters on the heap, and I notice there's quite a lot of arguments or differing in sort of how to set these. These would be the ones that you're probably most used to. And interestingly, it's not necessarily the higher you set it to the faster it goes. It doesn't always work like that. There are some things you can do, so let me just explain them. There's the XMS, which is the initial size of the heap that you get. And I'll go into the different types of heap in a second. And there's the XMX parameter, which is the maximum size. Now, let's assume they're both the same for the moment. Now, if it's very small, the JVM behaves differently because it's garbage collecting, obviously more frequently because you get close to the watermark and it garbage collects. It doesn't necessarily mean that your stuff runs any slower at all. It just runs in a different way. So one of the things you can try with this is to reduce your heap until you start to see a fairly notable difference. You can also monitor this on some of the tools, the JVisual VM, JStat, things like that, that you can monitor it with. But these are things to try, and this is the thing that's going to probably make a reasonable amount of difference to the way your code runs. Don't just give it 4 gig, or 8 gig, or 16 gig if you're running in a 64-bit VM. It doesn't necessarily make it go faster, and the big difference is that you really will notice is if you've got a lot of RAM in there, and you've set up your memory in the wrong way between your old memory and new memory, which I'll go into in a second, you end up with these complete garbage collections. Now, if you're garbage collecting 16 gigabytes of RAM and something running fast, your machine is going to halt, sometimes for several seconds. If you're running your machine across running TCP/IP connections, or you're expecting users to click on things, it will stop. Nothing will happen at all. I'm sure a few of you have seen this. So that's one of the problems with making it too big. Now, if you make MS and MX different, you'll see this graph on the top right. The orangey pink bit is the MX, or it's what's been actually used, and effectively it's going up to the top, to the peak. Now, if you set them both the same, what happens is that the memory is allocated immediately. Now, you might not need it, but if you're going to probably use it anyway, you might as well just give it to your Java VM anyway and let it run. The advantage of setting them both the same is that you get much more consistent results, because you don't know when this step is going to occur as it allocates more memory from the operating system. As you can see, those steps on the left-hand side of the pink bit as it goes up, that's the operating system handing more memory to it. So if you want it to run consistently, my personal preference is to set both of these the same. And if you're trying to do performance tuning, you get a consistent result each time. If you're running on a random machine in a user mode, obviously you don't want to grab all the memory all the time very quickly, so you tend to set MS lower than MX. But if you're running in a server, my preference would be to set them the same. Out of the heap, we divide this into 2 more sections. So we have the new generation and old generation. So what happens in this, and the new generation is then subdivided into 3 more sections, what's called Eden, and then the survivable. So effectively what happens, we have these mini garbage collectors, if you like. And so as your temporary, let's say, strings are allocated, what's happened is that they will be generated inside the Eden space. You'll get a mini garbage collector will come along, and it will move those into the survivable space. You've got 2 of those. Then effectively, eventually, once it does a garbage collection of those, any objects that survive, it'll eventually put those into the old area. Now, if you run out of that altogether, because you've got lots of garbage collections going, eventually what happens is you get an out of memory. And I'm sure every one of us, if you're working in Java, have seen that. Interesting thing is that you can actually set the difference between the old and the new. And this is probably the only other JVM parameter that, unless you really know what you're doing, tinkering around with the JVM, this is the only other parameter that you should probably experiment with. There is a default value per machine, per JVM, depending on whether you're running client or server, depending on the architecture, depending on the 32 or 64-bit. They tend to be somewhere around 4, 6, 8, 12, something like that. So depending on what you're running on, this new ratio will be set accordingly. But if you know you're running on a particular server, you're running on a 64-bit architecture, you know the way your program is behaving, and assuming you've optimized out all of the strings, as I pointed out earlier, you can start to experiment with this, and it will make quite a significant difference to the performance. I'm not talking a few percentage points. This could go up 50, possibly even more in terms of percentage of performance, because of the way that your allocations, if you're creating huge numbers of objects, you probably want to set new ratio down to something like 1 or 2. If it's any larger, then you effectively get a lot more large garbage collections coming. Now, just to give you an idea here, the XMX effectively gives you the new and the old. The slightly grayed bits are the bits of memory which are not yet allocated. So effectively it's there, it's allowed to use it, but it doesn't. So we've got the Eden, the survivable space, 2 of those, number 1 and 2, or to and from as they're sometimes called. You've got the old, which is also called tenured, and then the permgen. The permgen tends to stay fixed, as I said before. It either works or it doesn't work, or there is a small bit of garbage collection. And effectively, it's the new ratio that you can change on these. So this is probably those two parameters, the XMX, XMS, and new ratio, probably the three parameters are going to make the biggest difference to your machine. Finally, if you really want to go into a little bit more fine tuning, you can actually also set the ratio between the new, or the Eden, and the survivable space. And again, this is assuming that you've really analyzed your application. Most of the applications I've come across are way too complex and have too many different things going on to actually work out to this level whether we're going to get into this sort of level of tuning. And I found far better results from looking at the architecture, looking at the code, than getting into this level. So my warning here would be, if you're getting into this sort of level, you really need to know what you're doing. You need the sort of Kirk Pepperdines of the world to be able to reach this sort of level of tuning and actually get something useful out of it. I've got a couple more slides here now. There's a couple of tools. Now this is, again, before you get into tuning your VM, there are some things you need to do. Look at the architecture. Some of the points that I made before about the silly mistakes about putting too much memory into a machine, or not having enough memory in the machine, but putting too much on the VM, not overly complex solutions, writing stuff to complex, expensive solutions. Databases, people go over the top to use databases just because you have an official database. Everything's got to go onto Oracle, everything must go onto Sybase, or whatever it may be. Quite often disk is perfectly useful. Oracle stores it in a disk anyway, and all it is a mechanism. It's a big, complicated, and unbelievably expensive gadget that gives you an interface between your application and the disk. A lot of the stuff that you store can be written straight to disk. You can grep it, you can index it, you can create your own indexes. It works just as well. So assuming that you've been through your architecture, assuming that you've been through your code, finally you can start to get down to looking at the Java virtual machine and looking at the sort of performance you can get out of it. The tools you're going to be using, and I would hope there's a lot of people use here, JConsole, JVisualVM. That was a call for hands, a few of you, yep. These are tools that will really give you the ability to understand how your machine's being used. That graph that I put up earlier was just a cut and paste. In fact, someone else's cut and paste, but I've got some others that I was going to put on there. That one just looked nicer than mine. But it'll give you an idea as to how the memory is being used. You can look at how the threads are being used. All of these parameters, again, don't forget, if you're running multi-threaded, you need more memory. The memory is divided up per thread. So if your system runs in one thread and it needs minimum 64 meg of RAM, let's say we need 128, then if you've got 4 threads, then multiply that up. You're going to need 512 at least to run in 4 threads. If you're running 8, etc., you'll know how the maths works. So these are the sorts of parameters. At the bottom, we've got a large list. Now, I don't suggest you put all of these in one go, but these, obviously you'll get these slides afterwards, so you don't need to jot these things down. But these are things which give you quite an impressive list of information about how the garbage collector is working, and how that's working, again, in combination with something like JSTAT, will show you how the Java virtual machine has been used, how the space has been allocated, how the Eden space, the new, the old, etc., are being used within your machine. It'll give you a lot of information as to how to tune your application. One thing I've done typically is, well, get someone to look at the code, and you think, wow, we're generating that many objects? Why is this thing running so slow? Don't try and tune it at that point to suddenly say, oh, okay, we'll just change the new gen parameter, and go back to your application and see why you're using so many objects, see why you're getting so many objects. In a perfect world, you should be looking at object reuse, object pools, all sorts of things like this to try and bring these down. It's going to really make a huge difference to your application. So in closing up, if you really want more oomph is a wonderful English word, out of your application, which just implies everything, just more go. My recommendation, and again, this is over years and years, but it was really brought through to me in the last couple of weeks. Look at your architecture first. You're going to get a lot more out of your performance tuning from your architecture, particularly if you're working in a distributed architecture. If you've got transactions, seriously think about taking them out. People overuse transactions. You're looking 10 to 100 times worse performance. People get obsessed with transactions. Use compensational transactions, for example. ORM, object relational mapping, it just kills machines. You're going from an object-oriented world into a relational mapping world. The two of them just don't go together. So think about how you can change the architecture of that. So once you've been through this, once you've gone through these optimizations, look at the code, look at the Java virtual machine. The Java virtual machine will probably tell you more about how badly your code is written than in fact how badly the JVM is running. So take the messages from that, go back to your code, modify your code, and then come back to the JVM. When you're absolutely sure it's perfect, then start applying some of these JVM tips. I think that's pretty much it. Thank you very much. Any questions at all? Nothing at all? Oh yes, I have one over here. I'm not an expert, to be honest, on the changes. I still have two very large clients who I think I'll embarrass and name, people like the Federal Reserve Bank and these sorts of places which are still running on Java 1.4. When I was at JP Morgan Chase, we managed to justify using Java 1.5, or 5 as it's called now, purely on the 21% performance gain. The saving was in the well over $10 million in terms of saving. So the clients that we have typically, for the code that we generate, we had to be very careful not to go much past 5. I have Java 1.7, I'm using Java 1.7, but unfortunately for my usage, it tends to be a sort of a pipe dream to be able to put it into something else. So I'm afraid I'm not an expert on the changes other than the sort of nice new features. So I'm sorry, I can't give you a huge amount of information on that. But I know some colleagues who can. If you're interested, I can put you in touch. Another question here? So the question was looking at the sort of optimizations which I had there on bytes and strings. They were meant to be sort of an example. The examples were sort of typical code that I found. What are the recommendations for XML parsing? I must admit I'm slightly biased on this one because one of my companies is C24, which is outside, and effectively the way it's one of the solutions. Effectively, it's like Java binding. So JAX-B, JIBX, are these typical products that take an XML schema. They create an exact Java mapping to that and effectively parse it. There's a lot of things when you get involved in XML, obviously, that you want to be careful of. One is performance. I'm sure you're well aware and familiar with differences between DOM, Java binding, and SAX parsers, for example. If you're just taking information out of it, SAX parsers far quicker. If you're taking lots of information out, you end up parsing it multiple times. Then you've got validation to worry about and things like that. So if I had a sales hat on, which I don't because I'm a CTO rather than a salesperson, I would say go over to the C24 counter and have a look on there. It's our clients and the ones that I'm representing here use that product to do their complex XML parsing. So that includes the sort of ISO 20022, FPML, those sorts of things. There are things that will parse it quicker. There is nothing I know of that will validate it quicker. When I talk about validation, I mean beyond schema validation. We still use something like Xerces for schema validation. So it's not a one-off simple answer, but that hopefully give you some idea. Any more questions? Yeah, over here. Closures and what have you. Yeah, did everyone hear that? I heard it perfectly. What's wrong with your ears? Somebody with a foreign accent similar to mine, but much further south by the sounds of it, who obviously knows an awful lot more about Java 7 than I do. It's talking about the advice in a concurrent architecture, and concurrency is actually, if I sort of understood you right, is actually more towards, or the performance is more towards generating lots of small objects. When you've got things like closures where the functions are effectively generating classes as well. And then you've got things like the concurrent garbage collector, which comes along as well. So again, this isn't a one-off piece of advice, don't use lots of objects. This was a piece of advice for the situation that we had in particular on this particular one. Obviously, we do run multi-threaded, and this particular problem that we had was in the object creation. So, sorry, what's your name? Josh. Oh, yes, Josh, yes. I saw you outside. So, Josh, if you want to ask questions, he's sitting over there. Any more? More questions? You had a question, or was that? Visual GC plugin?
Yeah, so it does a lot of that. It's very nice on that.
Okay, so Visual GC plugin for the JVM. I did notice a lot of plugins, so it's obviously one of the ones to use. Gives you a lot of good.
So it was actually a question as well as on stack.
So thread stack size, how do we optimize that? It's difficult. I think anybody working in a multi-threaded environment will tell you it's one of those hit and miss things. As soon as you start looking into the threads, it becomes a bit like sort of Heisenberg's uncertainty principle. As soon as you start looking at it, everything changes, and you try and hit something. My experience is purely hit and miss on that side. Again, it's the sort of thing that we engage people like Martin and Kirk Pepperdine to basically look into these sort of things for literally a month to work on this. And those guys run quite a lot of courses on the really deep level performance tuning. Any more questions at all? One over here. That's impressive. So he has a stop the world garbage collection for 30 seconds. Actually, I'd like to take that and use that as an example. That's an impressive one. 30-second garbage collection. And how would I go about stopping it? You can take snapshots, so you can use a lot of these tools effectively to take snapshots. And my advice on this would be your old memory is obviously getting used far too quickly. So something as simple as looking at the new ratio might start helping you with this, but effectively the tools will give you a much better view of what's going on inside them. Some of the parameters that you had up there, just before embarrassing screensavers come up. Put this back on. You get lots of pictures of my kids otherwise. The tools will give you a lot of information. You can do complete memory dumps, heap dumps, etc. That would give you some sort of visualization as to what's going on inside. And those are things which you can run on if you run the JStat, for example, you can run that every second or more. You can effectively see how your memory usage is being used up. That would imply effectively, depending whether you're running server or client mode on the JVM, depending on the ratio, effectively what's happening is you're probably filling up your old generation, which is I would imagine, fairly large if you're getting 30 seconds. What have you got, 16 gig or more?
No,
1 gig. You've got a very slow machine then. Or it's busy. Is it multi-threaded? Yeah, it's the problem with a lot of these things is when you start to really get close to the limits, you've got the virtual machine sort of competing with the garbage collectors. Sorry, you've got the garbage collector competing with your application as well, and you'll get lots of mini garbage collections as well. There's no one answer for that. Maybe you'll find the concurrent garbage collector will pick up stuff quicker. I would suggest the initial things to look at would be trying to get an idea of your heap usage and looking at the different ratios of the new generation to the old generation. but you should be able to knock that down quite considerably. I would hope to under a second. Any more questions? How are we doing for time? We're good for time, so thank you very much.